Welcome to HKDF. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are diving into RFC 5869, which describes HKDF, the HMAC-based Key Derivation Function. Now, if that sounds intimidating, do not worry. I am going to break this down in a way that anyone can understand. Think of HKDF as a special kitchen appliance that takes raw ingredients and transforms them into multiple different finished products. Just like you can take flour, water, and yeast to make bread, rolls, and pizza dough, HKDF takes one piece of secret key material and stretches it into multiple cryptographic keys that can be used for different purposes. This is incredibly useful in real-world security applications because you often need several different keys, one for encryption, one for authentication, maybe another for integrity checking, but you only have one shared secret to start with. HKDF was published in May 2010 and has become a fundamental building block in modern cryptography, used in protocols like TLS 1.3, signal messaging, and many others. The problem HKDF solves. Before we understand what HKDF does, we need to understand the problem it solves. Imagine you are building a secure messaging application. You and your friend establish a shared secret, maybe through a key exchange like Diffie-Hellman. Great, but here is the thing. You cannot just use that raw shared secret directly for encryption. Why? Because that shared secret might not have perfect randomness, it might be the wrong length for your encryption algorithm, or it might have some mathematical properties that make it weak. It is like having a rough diamond that needs to be cut and polished before it can be used in jewelry. Furthermore, you actually need multiple keys. One to encrypt messages going from you to your friend, another for messages from your friend to you, maybe another for message authentication codes, and perhaps one more for deriving future keys. If you just used the same key for everything, you would be creating security vulnerabilities. The traditional approach was to use a key derivation function, but different systems implemented this differently, leading to inconsistencies and potential security flaws. RFC 5869 standardized this process through HKDF. HKDF overview and components. HKDF is actually composed of two distinct functions working together: extract and expand. Think of it like a two-stage factory process. The extract stage takes your raw input key material, which might be messy, too long, too short, or not perfectly random, and produces a fixed-length pseudo-random key. This is like taking raw ore and smelting it down into a pure metal ingot. The expand stage then takes that pseudo-random key and stretches it into as many cryptographic keys as you need, each of a specific length. This is like taking that metal ingot and casting it into many different shaped tools. Both stages use HMAC as their underlying cryptographic primitive. HMAC stands for Hash-Based Message Authentication Code, and it is a well-studied, secure function that combines a cryptographic hash function with a secret key. The beauty of HKDF is its flexibility. You can use it with different hash functions like SHA-256, SHA-384, or SHA-512, depending on your security requirements. The RFC does not mandate one specific hash function. Instead, it provides a framework that works with any cryptographic hash function you choose. HKDF Extract Phase Deep Dive. Let's zoom into the extract phase and really understand what's happening here. The extract function takes three inputs. First is your input key material, abbreviated as IKM. This is your raw secret that might come from a key exchange, a password, or any other source. Second is a salt value, which is optional but highly recommended. The salt is like adding seasoning to your cooking. It doesn't need to be secret, but it should be random and unique for each use. If you don't provide a salt, HKDF uses a string of zeros. Third is the choice of hash function, which determines the output length. The extract function performs a simple but powerful operation. It computes PRK equals HMAC hash with salt as the key, applied to the IKM. The output, called PRK for pseudorandom key, is a fixed length value that has excellent cryptographic properties. It's uniformly random, it's unpredictable, and it's the perfect length for the hash function you chose. For example, if you use SHA-256, your PRK will be exactly 256 bits or 32 bytes long. The extract phase essentially concentrates all the entropy from your input material into a compact, high-quality pseudorandom key, regardless of how messy or imperfect your original input was. HKDF Expand Phase Deep Dive. Now that we have our purified pseudorandom key from the extract phase, we move to the expand phase, which is where the real magic happens. The expand function takes the PRK we just created and generates as much key material as we need, potentially much more than the original PRK length. Think of it like a seed that grows into a tree with many branches. The expand function takes 4 inputs: the PRK from extract, an optional context info parameter, the desired output length L, and the hash function. The info parameter is particularly interesting. It allows you to generate different keys for different purposes from the same PRK. For example, you might use info equals client encryption key for one purpose and info equals server encryption key for another, ensuring you get completely different keys. The expand function works iteratively. It produces output in blocks, where each block is computed using HMAC with the PRK as the key. The first block is HMAC hash applied to the info concatenated with the byte value 1. The second block includes the previous block in its computation, creating a chain. This continues until we have generated enough output to reach the desired length L. The maximum length you can generate is 255 times the hash length, which gives you plenty of room. For SHA-256, that is 8,160 bytes of derived key material. How extract and expand work together. Understanding how extract and expand work together as a complete system is crucial. The extract phase is all about quality. It takes potentially weak or non-uniform input and produces high-quality cryptographic material. The expand phase is all about quantity. It takes that high-quality material and generates as much key data as needed. Together, they form a robust key derivation system. Here's a real-world analogy. Imagine you're making fruit juice concentrate. The extract phase is like pressing fresh fruits and reducing them down to a concentrated syrup that captures all the flavor and nutrients in a compact form. The expand phase is like adding water back to that concentrate, but in a controlled way, to create exactly the amount of juice you need, with consistent quality throughout. In cryptographic terms, extract ensures that even if your input key material came from a weak source, the output PRK is cryptographically strong. Expand ensures that all the derived keys are computationally independent. Knowing one derived key does not help an attacker figure out any other derived keys. This separation of concerns makes HKDF both secure and flexible. You can even skip the extract phase if your input key material is already a uniformly random string of the right length, though using both phases is generally recommended for maximum security. Inputs and parameters explained. Let's break down all the inputs and parameters you'll work with when using HKDF, because understanding these is key to using HKDF correctly in your applications. First, there's the input key material, or IKM. This is your starting secret. It could be the output of a Diffie-Hellman key exchange, a shared password that's been through some processing, or any other secret value. The IKM doesn't need to be perfectly random, and it can be any length. Second, we have the salt parameter. While optional, using a salt is strongly recommended because it provides domain separation and strengthens the extraction of randomness from IKM. The salt should be a random or pseudorandom value, ideally as long as the hash output length, but it doesn't need to be kept secret. If you're deriving keys for different sessions or contexts, Use a different salt for each. Third is the info parameter, which is used in the expand phase. This is completely optional and can be an empty string, but it's incredibly useful for generating multiple different keys from the same PRK. You might include protocol names, user identifiers, or purpose labels in the info parameter. Fourth is the length parameter L, which specifies how many bytes of output key material you want from the expand phase. Finally, you need to specify which hash function to use throughout. Common choices are SHA-256 for general use, SHA-384 or SHA-512 for higher security applications, or even SHA-1 if you're working with legacy systems, though that's not recommended for new designs. Step-by-step HKDF process. Let me walk you through a complete HKDF operation, step by step, so you can see exactly how everything flows together. Step 1. Gather your inputs. You need your input key material. Decide on a salt value, or let it default to zeros. Prepare your info string if you want domain separation. Choose your hash function, and determine how many bytes of output you need. Step 2. Execute the extract phase. Compute PRK equals HMAC hash with the salt as the HMAC key, and IKM as the message. This gives you a fixed length pseudorandom key. For example, with SHA-256, you will get exactly 32 bytes. Step 3. Begin the expand phase. Initialize an empty output string and set a counter to 1. Step 4. Generate the first output block by computing HMAC hash with PRK as the key, and the message being your info parameter concatenated with the byte value 1. Append this to your output. Step 5. If you need more output, generate the next block by computing HMAC hash with PRK as the key, and the message being the previous block concatenated with info concatenated with counter value 2. Continue this process, incrementing the counter each time. Step 6. Once your output string is at least as long as the desired length L, truncate it to exactly L bytes. That is your final derived key material. You can now split this output into separate keys for different purposes. Security properties and guarantees. One of the most important aspects of HKDF is understanding its security properties and what guarantees it provides. HKDF has been formally analyzed by cryptographers and proven to meet specific security definitions. First, the extract phase provides a property called randomness extraction. This means that even if your input key material has weaknesses, for example, it is biased, or it is from a source with limited entropy, the extract phase will produce output that is computationally indistinguishable from truly random data. This is crucial because real-world key sources are rarely perfect. Second, the expand phase provides pseudorandom generation. Given the PRK, an attacker who does not know the PRK cannot distinguish the expanded output from random data, even if they know the info parameter and can see some of the output. Third, HKDF provides computational independence between derived keys. If an attacker learns one derived key, they cannot use that information to figure out other keys derived from the same PRK with different info values. Fourth, HKDF is forward secure in the sense that compromise of derived keys does not reveal the PRK. These security properties rely on the underlying strength of HMAC and the hash function you choose. As long as your hash function remains secure against collision and preimage attacks, HKDF remains secure. The beauty is that HKDF's security has been proven mathematically under reasonable assumptions about HMAC, so you are not relying on ad hoc designs. Real-world example TLS handshake. Let's look at a concrete, real-world example of where HKDF is used. The TLS 1.3 handshake. When you connect to a secure website using HTTPS, your browser and the web server need to establish several cryptographic keys. They perform an elliptic curve Diffie-Hellman key exchange, which gives them a shared secret. This becomes the IKM for HKDF. The TLS protocol uses HKDF extract with a salt derived from the handshake transcript to produce a PRK called the handshake secret. Then, using HKDF expand with different info values, TLS derives separate keys for client-to-server encryption, server-to-client encryption, client-to-server authentication, and server-to-client authentication. Each of these keys is completely independent but derived from the same handshake secret. As the handshake progresses, TLS performs additional HKDF operations to derive the master secret and eventually the application traffic keys that protect your actual data. By using different info strings at each stage, for example, client handshake traffic secret or server application traffic secret, TLS ensures that keys used for different purposes and different stages of the connection are cryptographically separated. This prevents cross-protocol attacks and provides clean security boundaries. The use of HKDF in TLS 1.3 is one reason why the protocol is considered more robust than earlier TLS versions. Common use cases. HKDF is used in numerous cryptographic protocols and applications beyond just TLS. Let's explore some common use cases. First, secure messaging applications like Signal use HKDF to derive message keys from conversation keys, ensuring that each message is encrypted with a unique key. This provides forward secrecy, meaning if one message key is compromised, previous and future messages remain secure. Second, VPN protocols use HKDF to derive encryption and authentication keys from the master secret established during connection setup. Third, password-based key derivation systems use HKDF as a final step after running the password through a computationally expensive function like PBKDF2 or Argon2. Fourth, IoT devices use HKDF to derive device-specific keys from a master key, allowing unique credentials for millions of devices while only storing one master key in the manufacturing system. Fifth, cloud encryption systems use HKDF to derive data encryption keys from a master key managed by a key management service, enabling secure key rotation and hierarchical key management. Sixth, wireless protocols like Wi-Fi protected access use HKDF to derive pairwise keys from the pre-shared key or from keys established during authentication. In all these cases, HKDF provides a standardized, secure, and efficient way to transform one key into many, with formal security guarantees that give protocol designers confidence in their security architecture. Choosing the right hash function. When implementing HKDF, one of the first decisions you will make is which hash function to use. This choice impacts both security and performance. The most common choice today is SHA-256. This provides 256 bits of security, which is considered strong for the foreseeable future. SHA-256 is widely supported, fast on most hardware, and has been extensively analyzed by cryptographers. If you need higher security margins, for example, for long-term secret protection or in a high-value environment, you might choose SHA-384 or SHA-512. These provide 384 and 512 bits of output respectively, though their actual security strength is calculated differently. SHA-512 is particularly efficient on 64-bit processors. For legacy systems, you might encounter SHA-1, but this is not recommended for new designs due to known collision vulnerabilities with SHA-1. While HKDF with SHA-1 might still be secure for key derivation, using SHA-256 or better avoids potential future problems. Some modern systems use SHA-3 or BLAKE2, which are newer hash functions with different design principles than the SHA-2 family. The key consideration is that your hash function should be collision-resistant and behave like a random oracle. Your choice also determines the maximum output length of HKDF expand. You can generate up to 255 times the hash length. For SHA-256, that is 8160 bytes, which is more than sufficient for most applications. Implementation considerations. When you are implementing HKDF in your own code or configuring it within a library, there are several practical considerations to keep in mind. First, decide whether you need both extract and expand, or just expand. If your IKM is already a uniformly random key of the proper length, perhaps it is the output of another KDF or a hardware random number generator, you might skip extract. However, using both phases is generally recommended for defense in depth. Second, carefully manage your salt values. In many protocols, the salt is derived from a handshake transcript or session identifier. Make sure your salt is unique for each session or context where you are using HKDF. Third, be deliberate about your info strings. These should clearly identify the purpose of each derived key. Use a structured format like protocol name pipe key purpose pipe context identifier. This prevents key reuse across different contexts. Fourth, be careful about output length. Only request as much output as you actually need. There is no security benefit to generating extra key material and discarding it. Fifth, use constant time implementations of HMAC to prevent timing attacks, especially if your IKM or PRK might be partially controlled by an attacker. Sixth, consider using test vectors from RFC 5869 to validate your implementation. The RFC provides several test cases with SHA-256 and SHA-1 that you can use to ensure your code matches the specification exactly. Finally, remember that HKDF is not a password hashing function. Do not use it directly on passwords without first applying a proper password hashing function like PBKDF2, Argon2, or script. Mathematical foundation. Let's dive a bit deeper into the mathematical foundations of HKDF, though we will keep this accessible. HKDF security is based on the assumption that HMAC behaves like a pseudorandom function, or PRF. A PRF is a function that, when keyed with a secret key, produces output that is computationally indistinguishable from truly random values. HMAC itself is built on top of a cryptographic hash function, using a construction that involves two hash operations with different key-derived constants. The security proof of HKDF, published in the academic paper by Hugo Kravchuk, shows that if HMAC is a good PRF, then HKDF extract produces output that is computationally close to uniform random. And HKDF expand produces output that is indistinguishable from random given knowledge of the info parameter, but not the PRK. The proof uses concepts from computational complexity theory and reduction arguments, essentially showing that breaking HKDF would require breaking HMAC. The extract phase is proven secure under the assumption that HMAC behaves like a randomness extractor, which is a function that can pull uniform randomness from a weakly random source. The expand phase security relies on HMAC being a secure PRF and on the counter-based construction that chains blocks together. The mathematical beauty of HKDF is that it achieves strong security with minimal computational overhead, just a small number of HMAC operations proportional to the output length you need. Test vectors and validation. RFC 5869 includes several test vectors that are absolutely critical for validating implementations. Let me explain what these are and why they matter. A test vector is a set of known inputs and the corresponding expected outputs. If you implement HKDF and run it with the test vector inputs, you should get exactly the same outputs as specified in the RFC. This proves your implementation matches the specification. The RFC provides test cases for both SHA-256 and SHA-1. Let me walk through test case 1, which uses SHA-256. The IKM is a 22-byte hexadecimal string starting with beginning with 0x0b ending with 0b. The salt is a 13-byte string of hex values. The info is a 10-byte string. The output length L is 42 bytes. The RFC specifies the exact PRK that should result from HKDF extract, and the exact 42-byte output key material from HKDF expand. Test case 2 uses longer inputs with 80 bytes of IKM, and generates 82 bytes of output. Test case 3 demonstrates the case where salt is omitted, defaulting to zeros. There are also test cases with SHA-1. When implementing HKDF, you should run all these test vectors and verify your outputs match byte for byte. Any deviation means there is a bug in your implementation. Many cryptographic libraries include these test vectors in their unit tests. If you are reviewing or auditing HKDF code, checking that it passes the RFC test vectors is a basic but essential verification step. Conclusion and key takeaways. Let's wrap up with the key takeaways about HKDF first. HKDF is a standardized, well-analyzed key derivation function that transforms one secret key into multiple derived keys. It consists of two phases. Extract purifies input key material into a pseudorandom key, while expand generates as much output key material as needed. Second, HKDF is flexible, working with any cryptographic hash function, though SHA-256 is recommended for most applications. Third, the security of HKDF is proven under reasonable assumptions about HMAC and has been extensively analyzed by cryptographers. Fourth, HKDF is efficient and practical for everything from embedded systems to high-performance servers. Fifth, HKDF is widely deployed in real-world protocols like TLS 1.3, Signal, and many others, proving its practical utility. When using HKDF, remember to use different salts for different contexts. Use meaningful info strings to separate keys by purpose. Choose an appropriate hash function, and validate your implementation with RFC test vectors. Don't use HKDF directly on passwords. Process them with a password hashing function first. HKDF is a building block, not a complete solution. You still need to use the derived keys properly with authenticated encryption or MAC algorithms. Understanding HKDF gives you insight into how modern cryptographic protocols derive the multiple keys they need from limited shared secrets. Whether you're implementing security protocols, building secure applications, or just trying to understand how systems like TLS work under the hood, HKDF is an essential concept to master. Thank you for your attendance. Please consider subscribing to the channel.